How's it going, everyone? Mr. Geyser here with the video for our Lesson A on the secant, cosecant, and cotangent functions. We have four main skills and learning objectives. First, we want to try and graph that secant, cosecant, and cotangent functions. Second, we want to try and find the period and amplitude for one cycle of these periodic functions. Three, we want to describe the key characteristics of these periodic reciprocal functions. And four, we want to graph the transformation of these reciprocal functions. Let's revisit the unit circle in order to introduce the remaining three reciprocal trigonometric functions. We will investigate the reciprocals of sine, cosine, and tangent functions, their properties, and their graphs. We obtained the graphs of cotangent, cosecant, and secant curves by using the reciprocal identities below, where our cotangent refers to the reciprocal of tangent, our cosecant refers to the reciprocal of our sine value, and our secant x refers to our reciprocal for cosine x. For example 1, in the sketch to the left, theta is in standard position and point P, x and y, is a point on the unit circle that corresponds to theta. We want to complete the following table here in terms of x and y. So no numbers real quick, and a lot of this is just quick review, where our sine of theta here is just that vertical displacement, but our cosecant here is that reciprocal for our vertical displacement. For our terms of cosine and secant here, cosine is just our horizontal displacement, while our secant is going to be the reciprocal of that horizontal displacement. Tangent, though, is just the slope of that terminal ray. Our sine and cosine are lengths of these values. So this vertical displacement is the length of that red line. This blue line, or the blue section here for the horizontal displacement, this x value is the length of that line for cosine here. Tangent and cotangent are the weird ones. These are not lengths of values, rather they're the slope of the terminal ray, so they're a ratio of some kind. They're specifically the slope of that ray to that point where x and y correspond to cosine and sine. For the domain and range of these trigonometric functions, we have four trigonometric functions of sine, cosine, cosecant, and secant. A revolution of one circle for a system of 2 pi, or for a cycle of 2 pi, will result in the same output for these functions. For tangent and cotangent, only a half revolution of pi will result in the same outputs, meaning that once we revolve around around the unit circle in 2 pi, these values repeat for sine, cosine, secant, and cosecant. For tangent and cotangent, we only need to go halfway around the unit circle for these values here to repeat. So let's first just bring in sine and cosine here. For our undefined points between 0 and 2 pi, sine and cosine, they're always valid inside that unit circle. For this domain here, we're able to plug in any of those values, but the range is restricted for sine and cosine, mainly because we can only reach -1 at the lowest and +1 at the highest. Tangent is a little bit different. Tangent here, it is undefined at these two key points. And really, it's undefined here because for that ratio, cosine is 0. If cosine, the value in the denominator of that ratio, is 0, these points here become undefined. For this domain here, it's just showcasing that repeating value every pi, where every pi and a half times pi, or times 1 for these integers here, you're going to have one of those vertical asymptotes. The range, though, is different. Our range for tangent is any real number. So we can't plug in every number into tangent, but we will get out some value for any number for tangent here. If we now look at cosecant and secant here, cosecant and secant correspond to sine and cosine, where cosecant and sine almost have an inverse reciprocal relationship, where our points here, where 0 and pi are undefined for cosecant, is where sine is 0. So for that reciprocal kind of fraction, when sine is 0, our cosecant is going to be undefined. We can write this equation here, where every value of pi times some integer will give us one of those vertical asymptotes. And our ranges here also feel reciprocal or inverse to our sine and cosine, where the range goes from -infinity up into -1, then goes from 1 to +infinity. Same kind of idea for secant here. Secant corresponds to cosine, where secant happens to be undefined whenever cosine is equal to 0 here. And I want you guys to notice that secant and tangent have the same values when they're undefined, with cosecant and cotangent also having the same values where it's undefined for the same reason. For cosecant and cotangent, that's when the sine value is in the denominator. So whenever sine is 0, cosecant and cotangent will be undefined. Whenever cosine is 0, that's when tangent and secant are undefined. We're able to write out these inverse domain values where theta is not valid, while all other values are valid. And again, for tangent and cotangent, those values or their range values are positive infinity to negative infinity, any real numbers for the range for these two here. Now let's take a look at the cosecant and secant functions are reciprocal functions. We want to try and graph them here on these grids to the right. We can use the concepts as an aid in graphing, with the reciprocal functions behaving as sort of a skeleton for the graph in question. What I mean to say is, if we look at cosecant here, cosecant corresponds to sine value, and all these domains and ranges are just coming from that previous slide. And we want to use the skeleton of the graph for sine here to help us graph its reciprocal function. When we have this sine graph here, just a normal sine of x graph, we then can plot all these vertical asymptotes where we know that cosecant is invalid. Now I want you to make a guess, just for a moment, as to think what the actual graph will be for cosecant. Hold it in your head. Do you think it would look like this? These flip-flopping parabolic curves? Yeah, it's a kind of a weird graph. Cosecant and secant are these flip-flopping parabolas where the only shared values are those maximum and minimums of its reciprocal function. So for cosecant and sine, the only times where they happen to equal each other are at these maximum and minimum values. Let's explore this again in one more example for secant. Secant here is going to correspond to our cosine values here, or our cosine functions here. This domain, range, and asymptote were just brought back from that previous slide. Our first step again in graphing secant here really is to graph the parent function, or the reciprocal function, I mean, and graphing its vertical asymptotes in these windows. Now, for these windows here, we want to graph these minimum and maximum values in these flip-flopping parabolic ways. For secant and cosecant are the reciprocal values of these periodic graphs. And it might feel unintuitive that these are the reciprocals, but as long as we have these zero values in the intercept for the midline of our reciprocal function, we'll be able to identify those windows of validity for those reciprocal values. Now, in example 1, we want to use transformations to graph each function, its reciprocal, state its domain, and show all of our asymptotes. In part A here, we're given this graph of y equals 2 cosecant of x over 2. We know that cosecant corresponds to that reciprocal of sine, where that reciprocal function is just replacing that trigonometric value of cosecant into sine. And we can find the period of this function here, its reciprocal, by just plugging in that 1/2 as b into that period function there. We find the period here as 4 pi, and now we're able to graph this reciprocal function here. Now notice that each of these intercepts along its midline is where we're going to place our vertical asymptotes. And now that we know where all the windows of validity are for our cosecant value, we can now graph those flip-flopping periodic functions at these maximum and minimum values for the reciprocal function of cosecant here. So it's almost like we're graphing the reciprocal of cosecant, being sine, where cosecant's the reciprocal of sine as well. And then we're graphing this value based off of the skeleton of this known function. Let's try that one more time in part B here. We want to graph y is equal to -2 secant 3x. First, that reciprocal function here is just replacing secant with cosine. And we can find the period by plugging in 3 for our b value into this periodic function here, where the period for this reciprocal and this graph here is going to be 2 pi over 3. That next step is to graph our reciprocal function and each of those intercepts here for that vertical asymptotes. And now we just grab the maximum and minimum values and place those parabolas. These black graphs here are the actual graphs for our secant and our cosecant values. We use the skeleton of sine, the skeleton of cosine to graph these functions here to help us identify where these maximum and minimum values are. In example 3, we want to try and explore cotangent, where the graph of cotangent functions will also complete one full cycle in the interval of 0 to pi. So its period of y equaling cotangent of theta is just pi. We're given this base equation here for cotangent, where it's exactly the same as our tangent function, where a is going to correspond to the amplitude, b is just the coefficient in front of our x value, c is still that phase shift, and d on the end here is just that vertical shift. Now notice on the right here, tangent is graphed first, and second is going to be cotangent. And I want to flip-flop back between these graphs a little bit to kind of see some patterns that emerge here, where each of its intercepts across the x-axis here is still its midline, but notice that the two key points of cotangent here are shared with tangent here, where tangent itself is almost trading those second key points here between two other graphs of cotangent. Another way to look at this too is that tangent here is always increasing across these wave intervals, while cotangent is going to be decreasing constantly across these wave intervals. We can now try and grab some of their domain and range values for cotangent. Our domain and range is very similar to tangent, but it's just shifted pi over 2. What I mean to say is for cotangent, its domain is whenever x isn't equal to some pi times an integer value here. Our range is still the same as tangent from positive infinity to negative, or from negative infinity to positive infinity, where those intercept values occur a pi and a half shift over compared to tangent. We can go back to that flip-flopping pattern real quick here, where our tangent values, its intercepts are at this value of 0 here, and then cotangent is really shifted over by a pi over 2. For tangent, its interval where it's valid, its domain, is from negative pi over 2 to positive pi over 2, while for cotangent, it's just shifted over by that pi over 2. For its y-intercept here, we do end up having it as none, only because we have a vertical asymptote at the y-axis. So for the parent function of just cotangent x, there's no y-intercepts. And for the symmetry for cotangent, same as for tangent, it happens to have an odd symmetry about the origin, where its asymptotes is the actual equation of its exclusive domain value here. Finally, for example 4, we're going to use the transformations to graph each function, state the period, and show all the asymptotes. For both of these cotangent functions here, we're kind of going to treat them very similarly to graphing our tangent functions, where for cotangent of 2 of x, our first task is just to find the period, where b is just equal to 2, and then we plug that into that tangent and cotangent period version of this equation, where it's pi over b, not 2 pi over b. So the period for this function here is pi over 2. A is still equal to 1. That coefficient in front of cotangent here, that invisible 1 there. There's no phase shift, so there's no c value. There's no vertical translation. There's no d value. So now we almost treat this like we're graphing a tangent function. I know that for cotangent, its first point is going to be at this 0, 0. So I can place my first vertical asymptote at 0, 0, and then go in the positive and negative x's in the length of the period we found and place those vertical asymptotes. Once we've done that, we're basically finished with the math in regards to this problem. Now we just want to use that middle technique where we go to the middle points of all of these vertical asymptotes and place an intercept about its midline. The midline being y equals 0 because d equals 0. So in the middle of these vertical asymptotes, we place our first key point. Then we go to that first amplitude here, since we have a positive amplitude. Our next point is going to be up from it, and we go from the left to the right when we're graphing these values. What I mean to say is for that first amplitude there, since it's positive, we take the middle of its intercept across its midline and this vertical asymptote and place that second key point. We then go to the negative amplitude and then find the middle between the intercept and its next vertical asymptote here. Almost like we're going from left to right with these key points now. Once we have those three key points, we now just connect all of our graphs together to create this wave function for cotangent. Let's try this one final time with y equals negative cotangent of pi over 2x plus 1. Our first point here, or our first step here, is just to find period, kind of list those a through d values. Period, again, is just taking that b value of that coefficient in front of x, pi over 2, plug that into that equation, and find that the period is equal to 2. Our amplitude is still equal to 1 here, not negative 1. We just need to keep that in the back of our head that this is a negative equation. Our amplitude still is 1, though. That's a key point. Second, our change between our A and B graphs here is that we have a vertical shift, a vertical translation where D is equal to 1. That first step is still to graph that first key point of our vertical asymptote at 0, 0, as long as there's no phase shift, still 0. And then we go a full period length in the positive, a full period length in the negative, and place those vertical asymptotes. Now we would want to try and find the middle of these two vertical asymptotes next, but since we have a D value, we want to create that midline. Now that we have this midline, we now find the middle of these vertical asymptotes where we're placing it where it's intercepting that midline. So it's almost like this is the new x-axis. And now, since we have a negative cotangent here, our next point is to go down and then to graph the middle of its vertical asymptote to its intercept here in the bottom section of this middle part here. Then we go above with our amplitude, the negative amplitude, and we then graph that third final key point. Once we have these three key points here, we now just connect all of our dots here, and we're finished with graphing our cotangent functions. Thank you very much for joining me on this first lesson for cotangent, cosecant, and secant, where we learned how to use that skeleton method to graph our cosecant and secant, and we used the normal method of graphing a tangent for cotangents here. If you have any questions at all, please leave them in the comments down below. I look forward to seeing all of you guys in class. Take care.